Hello, everyone. Today, we're going to talk about water problems faced by scientists and engineers, and we're going to look at sensor networks as a way to help solve these water problems. So now I'm going to deliver a presentation where we can look at some of these water problems that are faced and think about these sensor networks. The title of my presentation here today is Engineers and Scientists Help Solving Water Problems Using Sensor Networks. My name is Professor Jimmy Fox. I'm a civil engineering professor at the University of Kentucky here in Lexington, Kentucky. And here I have a number of collaborators that helped build this presentation and these ideas over the years. So engineers and scientists help solve these water problems using sensor networks. And so today we're going to answer two questions. What water problems do engineers and scientists help solve? We're going to start to see some of these water problems and learn about them that engineers and scientists can help solve. Secondly, we're going to look at water sensor networks and how they can help engineers and scientists. First, let's look at these water problems that engineers and scientists help solve. Navigation. Engineers and scientists help us to navigate our waterways. Perhaps one of the most well-known navigational feats of the last century was the building of the Panama Canal. So here, to travel from New York City to San Francisco, it was necessary to travel by boat around the tip of South America, all the way from New York to San Francisco. It took about 13,000 miles of travel by boat back in the 1800s. From 1903 to 1914, the Panama Canal was constructed, and this cut the boat trip from New York City to San Francisco to 5,200 miles. So it provided a navigational path that allowed barges and ocean-going vessels to transport goods to the other side of the United States. Here we see a blow up of the canal zone from the Caribbean Sea to the Pacific Ocean, and this canal zone is in between North America and South America. So the Panama Canal, this is constructed using a series of locks and dams. And so essentially what we see here, going from the Caribbean Sea to the Pacific Ocean, one travels through lock number 1, lock number 2, lock number 3, across the Panama Canal, and then through locks 4, 5, and 6. And then in the bottom of this image, we can see the presence of those locks that are acting like elevators for these large ships. Essentially, the ship comes into the lock and the water on the left, and the water level raises up to the level of the next pool. And then the gates of the lock open and the ship goes into the next pool, travels through that pool to the next locks. And so then in that way, the ship can travel up to the elevation of the Panama Canal, through the canal, and then down the other side. Here we see a picture of the Panama Canal. We see essentially two pools. We see a lower pool in the foreground and the upper pool in the background. And then we see that lock. You can see the lock gates here in the middle of the page, the lock gates that open and close with the water level changing. Here we see a large ocean-going vessel in the lower left in the presence of a tugboat to help direct the ship. That ship can then come into this lock, the gates can close, and then it can be moved down to that lower level, that lower elevation of the next pool. Here's an image showing the large gates, the large gates, and we see here some folks on a boat in the bottom of the image. In the foreground, we see those gates opening. The ship can then travel into that lock, and then the water level can be dropped. The boat can slowly lower down to the level of the downstream pool. And then here we see an image of a boat traveling across the Panama Canal. So this was Panama Canal is really a famous engineering works, but we can also talk about locks and dams and navigation on the Ohio River. And so here we see an image from the Ohio River, and we see a barge. We see a barge transporting coal. And so this is one of the major commodities that's travels on the Ohio River, that's transported on the Ohio River. These coal barges transport this coal up and down the Ohio River. Here we see on the Ohio River the Emsworth Locks and Dam. On the left side of the image, we see the dam, and we see the lower pool in the background and the upper pool in the foreground. And then we see the locks on the right-hand side. Again, that elevator that can be used by the barges. So here I want to jump to a short video where we can look at how these locks are being used. And this video will just give us another image here where we can see how this lock is working and how this works as an elevator on our Ohio River, Mississippi River systems.
See this lock we're coming up on? It's one of about 200 locks in our country built in the 1930s. It's been here a long time, so it's easy to forget just how amazing it is. Locks are essentially elevators that enable navigation on our inland rivers. Our southbound tow enters the lock chamber with the downstream gate closed. The upstream gate then closes behind us. A valve in the lock wall opens. 60 million gallons of water leave the chamber, lowering our tow. After about 17 minutes, the water level in the chamber is the same height as the downstream river. We are on our way. Our 15 barge tow is 1/4 of a mile long. It won't fit in a 600-foot lock chamber built for steamboats, so we need to send our tow through the lock in 2 segments. This is dangerous work that leads to significant delays. Most of our locks have outlived their lifespan, causing delays and threatening safety. There is a plan to fix this. NESP is a long-term program of navigation improvements and ecological restoration for the upper Mississippi and Illinois waterways. Learn more about this critical program.
Excellent. Well, here we had the chance to see how that lock is working and transporting that vessel from an upper pool through a lower pool. And here we see one more image of New Cumberland Locks and Dams. The U.S. Army Corps of Engineers manages and maintains this lock system. And we'll talk a little bit more about this issue brought up in the video with respect to the repair of locks momentarily. There are 19 sets of locks and dams on the Ohio rivers that engineers and scientists maintain and monitor. And so here we can see those 19 pools from the Emsworth upper pool in Pennsylvania down to the lower pool at Olmsted in Illinois. And these red dashed lines are indicating the presence of the locks. Locks and dams, and behind each of them sits a pool, a slack water pool that is the Ohio River. So engineers and scientists need to rebuild and replace these Ohio River locks and dams. Here's a blueprint of the McAlpine construction that went underway a few years ago. This was replacement of the McAlpine locks near Louisville. The upstream gates of this new McAlpine lock were roughly 70 feet tall. So we see these large doors or gates that are the part of the locks. We can see this backhoe in the lower part of the figure, as well as these cherry pickers that just give us a sense of scale for these 70-foot tall gates. Here we see the downstream gates and just get a better sense of the size of the structure. The piers for the guiding wall leading out of the lock are shown, and construction was done from barges on the Ohio River. And here we can see the cofferdam around the lock system when it was under construction. What other problems do scientists and engineers help us to solve. Another problem that we see is the problem of flooding. And so one example of flooding on the Ohio River is the event that took place in March of 1997. Here's a radar image showing the concentration of precipitation of rainfall over the Ohio River Valley. So here the Ohio River Valley is running right along the line of where all these yellow and green and red and orange pixels are showing us the presence of precipitation of rainfall. Here we see a map that's showing the amount of rain that fell during the flood of March 1997. Here we had locations in Jefferson County near Louisville that had as much as a foot of rain, 1 foot of rain over the region, highly concentrated in that Ohio River Valley. And this was the result. Immense flooding. Here we see the city of Cincinnati. We see the old stadium, and we see the flood levels crossing into the city. Cincinnati was flooded, as was Louisville. Here we see a photo of Louisville, the city of Louisville, that's inundated with floodwaters. And so engineers and scientists help to control flooding on the Ohio River by regulating flow through the dams, by building levees and flood walls, by building effective drainage systems, and building reservoirs for temporary water storage. The United States Army Corps of Engineers built 539 miles of levees on the Ohio River and currently have over 100 flood protection projects in the Ohio River Basin. For example, here we see the Beargrass Creek pump station that redirects floodwaters away from homes and businesses. So these huge pump stations can move this water away from the homes and the businesses. And then here we see flood walls. For example, we see this flood wall around Huntington, West Virginia. We see the graduated ruler on the right that is essentially showing us the stage or the depth of water during flood times from the Ohio River. So here, to get to the top of this flood wall, the Ohio River would need to be at a depth of 71 feet, 71 feet of water for the flooding to occur. And then this flood wall will protect the city of Huntington. Here we see another flood wall that protects the city of Parkersburg, West Virginia. We can see that concrete flood wall all around these businesses and these industries. And then we see the Ohio River wrapping around, and we see it in a flood stage, but it's protected by this flood wall. Okay, another problem, water problem that engineers and scientists are helping to solve, really a newer problem, is that of harmful algal blooms. Harmful algal blooms, or HABs, occur when colonies of algae, which are simple plants that live in the sea and fresh water, grow out of control and produce toxic or harmful effects on people, fish, shellfish, marine mammals, and birds. Here we see an image of the Ohio River when a harmful algal bloom has occurred. So in this aerial image, we see one of those barges traveling down the Ohio River, and we see the Ohio River as this green river with high concentration of algae due to this harmful algal bloom. Here we see scientists studying the harmful algal bloom that occurred in 2015, and they're working to solve this problem through research and then proposed mitigation. But we can see in the images this green algae on one of the tributaries of the Ohio River on the left, another tributary of the Ohio River on the right, showing this proliferation of algae that's caused by this harmful algal bloom. We've talked quite a bit about different problems that engineers and scientists help solve. Now let's look at some water sensor networks that help engineers and scientists with their solutions. So a first sensor network that we can look at is river and stream gauges. River and stream gauges, which are going to allow us to measure the water flow rate. So to help solve navigation, flooding, and algae problems, water sensor networks can estimate water volumetric flow rate, or Q. Q is the symbol that we use to symbolize water volumetric flow rate. Q is equal to the volume of water passing a location divided by the time it takes for that water to pass that location. So for example, we can look at the Q of a garden hose. Here we see a woman using her garden hose, and the Q out of this garden hose will be the volume of water that passes out of the end of this hose over or divided by the time it takes for the water to come out of that hose. So for example, a typical garden hose will deliver 12 gallons of water over a 1 minute period. So if you take a stopwatch and you time for 1 minute, how much water comes out of that garden hose? 12 gallons per minute will come out of that garden hose. The hose can deliver 12 gallons per minute. And so this would be in 1 minute, that hose could fill up 12-gallon jugs that we see here on the lower right, these 12-gallon jugs on the right side of our figure. Now we look at the Ohio River flow rate. The Ohio River water flow rate is equal to an average of 118 million gallons per minute. 118 million gallons per minute. Here we see on the right the Ohio River that's joining into the Mississippi River proper over near Olmsted, Illinois. And so on the left, we see the upper Mississippi coming into the page, and on the right we have the Ohio River joining the upper Mississippi to form the Mississippi River. This dashed line, this black dashed line, is the location where we will measure the water volumetric flow rate. And so at this location, 118 million gallons of water pass that line per minute. 118 million gallons per minute. If we take an Olympic-sized swimming pool that is extended 8.6 miles, 8.6 miles long, almost 9 miles long, okay, this is the amount of water that passes that line every minute. Amazing. There again, every minute, every 1 minute, enough water to fill a 9-mile long swimming pool exits the Ohio River and enters the Mississippi River. When we measure the flow rate, when we measure the volumetric flow rate, we can do so at a cross section in the river, such as that dashed line that I showed previously, by dividing the river into sections and then calculating the velocity of each section, the velocity of water flowing in each section, multiplying it by the area of that section, and then summing all of those velocity times areas to give us a total volumetric flow rate. Here we show a gentleman that works for the United States Geological Survey. In this time-lapsed image, he is taking the velocity, he's using a propeller meter to measure the velocity as he moves across the river for each one of these segments. Now, the Ohio River is so large that a person cannot stand in the river and measure the velocity. Therefore, the USGS and the Army Corps of Engineers will use a boat. So here we see a boat, and then they will take that boat and they will travel across a transect. When they travel across that transect, they'll use an acoustic Doppler velocimeter or a velocity meter to measure the velocity across that transect. Here we see a velocity transect coming into view in the next image. So this is an example of those velocity transects that were measured for the Ohio River. And as we see these different velocity representations, the lighter colored orange on the sides is indicating slower velocity of water, while the purple in the center is giving us the highest velocity of the water. So this was an example of a velocity transect that can be multiplied by the area to estimate Q. Stage sensors allow us to estimate Q. So after measuring Q, Q can be related to river depth or stage to produce stage discharge curves that allow for continuous estimates of the water volumetric flow rate. Here we see a map of the United States, and each dot on this map indicates the location of a United States Geologic Survey sensor gauge. And so at all of these dots, they are measuring the continuous water depth and using that to estimate Q for our rivers. Now we can go ahead and click on one of these locations near Kentucky and West Virginia and Southern Ohio and Southern Indiana. Here we see a blow up. Here's Parkersburg and Charleston and Huntington and Lexington and Louisville. Now we can blow up further and we can see a site for South Elkhorn Creek near Lexington, Kentucky. We can click on Access Data, and this gives us an access to current and historical observations of the stage, which is used to estimate that volumetric discharge. And so we can go ahead and click on that current data, and we can see Q measured in cubic feet per second as estimated for South Elkhorn Creek near Midway, Kentucky, just to the west of Lexington here. And then this blue line is indicating how Q changes as a rainfall event occurs and causes flooding on the creek. Another tool that scientists and engineers are using to solve water problems is super gauges. So these super gauges really gives us the next generation of gauges that we can use. Here's a super gauge at a lock for the Ohio River tributary at Green River. And so this super gauge, we see the sensor box up on the top of the lock. And then when we zoom in and we look at that sensor gauge, all kinds of water parameters can be measured that can help us to understand these harmful algae blooms, for example. We can measure the turbidity, the water temperature, the acidity or pH, the conductivity of the water. And so this is really the next generation of gauges known as super gauges. Here's the super gauge network that's expanding across the Ohio River Basin. We see super gauges in Kentucky, one near Huntington, West Virginia, and we see super gauges in Indiana, Ohio, and part of Illinois. So again, engineers and scientists help us to solve these water problems using sensor networks. Today, we talked about two types of questions regarding water problems. One is, what water problems do engineers and scientists help solve? We looked at these locks and dams used for navigation. We talked about flooding, and we talked about harmful algal blooms. And then we talked about different sensor networks. We talked about sensor networks for measuring and estimating Q, and we talked about super gauges to look at water quality parameters. Thank you, everyone, and we really appreciate your attention today and appreciate talking to you today about these water problems that engineers and scientists are helping us to solve using sensor networks. Have a wonderful day.